Hi everyone, today we are going to cover a sequence and series for IIT JAM MS, and the topics are convergence of sequence, convergence of series, comparison test, ratio test and root test for convergence of a series. You can see the example of sequence and series. For sequence I have written that 1 comma 2 comma 3 comma 4 comma 5 comma dot dot dot. This way we can write a sequence, and for series we can write like 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus dot dot dot. So in a sequence it is in a set like format, but in series it's a in summation like format. For more mathematical representation, like you can see in the below that we have written a sequence n equals to 1 to infinity. So this is a sequence with the elements like a1 comma a2 comma a3 comma dot dot dot, where an are real numbers and n belongs to natural number. For series we can write summation n equals to 0 to infinity an. So this is equals to a0 plus a1 plus a2 plus a3 plus dot dot dot, where ans are the real numbers. And here don't worry about the n equals to 0. Depending on n, it can be n equals to 1 or n equals to 2, even n equals to 3. So for different series it can start from a different number. Now for an, if we say like an equals to 1 by n, then for sequence our sequence will be 1 comma 1 by 2 comma 1 by 3 comma 1 by 4. But for series our series will be like 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus dot dot dot. Convergence of a sequence. A sequence an is said to be convergent sequence if there exists an such that an minus l less than epsilon for all n greater than equals to n, where l is a finite number and epsilon greater than 0 is a very small number. To make it simple, we have created two graphs. You can see the x-axis is our n and the y-axis is an. So for both the graph, you can see that the red line is being parallel to x-axis after a certain time. So we can say that the an is converging to a fixed number. So we can say that the sequence an is convergent. In this graph, you can see that the graph is not being parallel to x-axis at any time. So this is a example of divergent sequence. Now to understand the definition of convergence by the graph, we can see that here we have n equals to capital N. After this, the an is being equal to L, small l. So our an is converges to L. So we can write like for n greater than capital N, an minus L is converging to 0, or the distance between an and L is being very small. So we can write like mod of an minus L less than epsilon, where epsilon is very small number. And or we can say that limit an where n tends to infinity equals to L. So this is the simplification of the definition of convergent. This is a very important property. If an is converging to L, then L is unique. So you can see that for the example 1 minus 1 1 minus 1 1 minus 1, this sequence is converging to 2 points 1 and minus 1. So this sequence will be a divergent sequence. And the second property is if an less than bn less than cn such that n converging to L and cn converging to L, then bn also converges to L. Let us see a few examples now. Like for this sequence 1 by n equals to 1 to infinity. So here we can say that an equals to 1 by n. So we find out the limits, and we can see that the limit is equals to 0. So this is a finite number, so we can say that this sequence is a convergent sequence and the convergent point is 0. Let us check for another sequence whose nth term is an equals to 2n square plus 3n plus 5 by 6n cube plus 10 square plus 6. So let us find out the limit first. So to get the limit, we are dividing numerator and denominator by n square, and we can see that uh, we have only 2 by 6 and other terms are 0. So this is a finite number, so we can say that the sequence with an where n equals to 1 to infinity is a convergent sequence. We have two types of convergence: absolutely convergent and conditionally convergent. Suppose an is a sequence, then if mod of an sequence mod of an is convergent, then we say that the sequence is absolutely convergent. For conditionally convergent, let an is convergent but mod of an and sequence is divergent, then we call it conditionally convergent. And similarly we can say this for series also. And there is a important theorem, like absolutely convergence implies convergence. So if a sequence is absolutely convergence, then it must be a convergent sequence also. A sequence can be bounded or unbounded, and bounded can be of two types, like one is bounded below and another one is bounded above. We call a sequence bounded below if every element of the sequence is greater than a fixed number. Like here we have written like an greater than equals to k for all n. And for bounded above, a sequence is bounded above if every element of the sequence is less than a fixed number. Here we have written that an is less than equals to k for all, and a sequence is bounded when the sequence hold the both the property bounded below and bounded above. A sequence can be monotonically decreasing or monotonically increasing. For any of this property, we can call a sequence a monotonic sequence. Now let's discuss about the monotonically decreasing. A sequence of n is monotonically decreasing when n greater than equals to n plus 1 for all, and a sequence is monotonically increasing when an plus 1 greater than equals to an for all n. These are few good properties to know for a sequence, and I request you to focus on the last property, like if a sequence is bounded and monotonic, then it is convergent. So you can say that if you can prove a sequence is bounded and it is monotonic, monotonically increasing or decreasing, then the sequence will be a convergent sequence. To understand the convergence of series, first of all we create the partial sums, like S0 equals to A0, S1 equals to A0 plus A1, S, S2 equals to A0 plus A1 plus A2. So we can create a sequence with the S0, S1, S2, S3. So we can say that if this sequence is a convergent sequence, then the series an is a convergent series. In a sequence we have seen that n is converging to L, where L is a finite number. But in a series, an when n tends to infinity, it will converge to to 0. For example, let for n greater than equals to capital N converging to L, then summation of an equals to a0 plus a1 plus dot 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 a capital N minus 1 plus a capital N plus a capital N plus 1 plus dot dot dot. So from the a capital N, all the elements are going to be L. So if L is not 0, then we have a infinite terms with L. So the sum of these infinite terms will be infinite. So our series is going to be divergent, but we have assumed that our series is convergent, so it is a contradiction. So L can't be a finite number other than 0. we are trying to cover some standard series. So the first example is GP series. We have seen this in our school also. So we know that a GP series is equals to a by 1 minus r, where a is the initial term and r is the common ratio, and it must satisfy the condition that 0 less than r less than 1. So the next example we can see of a GP series 1 plus 1 by 2 plus 1 by 2 square plus 1 by 2 cube plus dot dot dot. Here 1 is our initial term, the first term, and the 1 by 2 is our r common ratio. So we can see that the sum of the series is 2. So we can say that this GP series is a convergent series. P series, it's 1 by n to the power p, where p greater than equals to 0. This series will be convergent if p greater than 1, and it will be divergent if 0 less than p less than equals to 1. So for example, we can say a series with nth term 1 by n to the power 5 is a convergent series, since here 5 is greater than 1. Alternative series. So alternative series, we can see that we have a alternative sign, like plus a0 minus a1 plus a2 minus a3 plus dot dot dot, and here all the n's are, or ai's are positive numbers. This series will be a convergent series if mod of an is decreasing monotonically and limit n tends to infinity equals to 0. For example, we can see that 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus dot dot. This is a series of log 2. So this series is converging to log 2. And here we can see that 1, 1 by 2, 1 by 3, 1 by 4. These are in decreasing format, and the limit of the unit term is 0. So it's satisfying both the conditions. So it must be a convergent series, and we can see that it's a formula of log 2. So it's actually converging to log 2. We have 3 tests for convergence of a series: a comparison test, ratio test, root test, and we are going to describe all the tests. Let's start with the comparison test. Suppose a and bn two sequence such that a and bn greater than equals to 0 and an less than bn for all n. Then the test suggesting us that if if the series Bn is convergent, then An is convergent, and if the series An is divergent, then Bn is also divergent. Let's use this test. For example, like we have n square by n cube minus 4, this series. Suppose An equals to n square by n cube minus 4, and let Bn equals to n square minus n cube, which is equals to 1 by n. So here we can see that n cube minus 4 is less than n cube. So an must be greater than bn for all n. Now we can see that bn is a harmonic series, so this is a divergent series. Or even we can compare with the p series, like 1 by n to the power p, where here p is 1. So we can say that's why we also can say that this is a divergent series. So by the test we can say that since an is greater than bn, so if bn is divergent, then an is divergent, and here we can see that bn is divergent, so we can say that an is also divergent. Now check another example. Here n by n cube plus 4. So let's an equals to n by n cube plus 4 and bn equals to n by n cube. So n by n cube equals to 1 by n square. This is a p series with p equals to 2, which is greater than equals to 1. So we can say that the series with bn will be a convergent series. Even in left side we can see that n cube plus 4 is greater than n cube. So 1 by n cube plus 4 less than 1 by n cube. So n by n cube plus 4 is less than n by n cube. So n by n cube plus 4 is less than 1 by n square. So we can say an less than bn for all n. So by these two conditions we can say that the given series is a convergent series. Ratio test. Suppose summation an is a series such that an not equals to 0 for all n. Let L equals to limit n tends to infinity mod of an plus 1 by n. Then the first condition, if L less than 1, then the series is absolutely convergent. So we can say that series is convergent also. And the second condition is, if the L is greater than 1, the series will be a divergent series. And if L equals to 1, then the test fails. We can't conclude anything about the convergent or divergent here. I have collected this question from IIT JAM 2019. So let's check the series of root over xn plus 1 is convergent or not. We use ratio test here, so we will check an plus 1 by an. So here our an plus 1 term will be root over xn plus 1 xn plus 2 by root over xn plus 1. So the term xn plus 1 will be removed, so we can see that our final term is root over xn plus 2 by xn. Since xn is convergent, so xn plus 2 by xn will be a finite number, so root over of this will be also a finite for limit n tends to infinity. So by ratio test we can say that the given series is a convergent series. Root test. Suppose an is a series, let L equals to limit n tends to infinity nth root of mod of an, or we can write it like limit n tends to infinity mod of an of power of 1 by n. So here the first condition is, if L equals less than 1, it implies the series is absolutely convergent, and if L greater than 1, the series will be divergent. If L equals to 1, then the test fails. The conditions are similarly with the ratio test. Let's see example now. Like you can see that this example, 3n to the power 4 plus 2n plus 1 by 4n to the power 4 plus 3n plus 5 whole to the power n. So here we can see a power n. So root test will be a good fit for this example. So suppose an equals to the nth term. So an mod of an to the power 1 by n is our 3 into the power 4 plus 2n plus 1 by 4 into the power 4 plus 3n plus 5. So let's take a limit n tends to infinity. Now let's divide the numerator and denominator by n to the power 4. So we can see that we have a 3 by 4 only, which is less than 1. So our series is a convergent series.